The following simulation shows you the magnetic induction from a solenoid. So in this video, we'll be discussing about the magnetic field and especially in the steady state condition. So before we get started, please check the notes in the description for the notes throughout this entire discussion, as well as the timestamps for you to skip through just in case if you want to study a very particular topic. So let's just jump straight away to what is magnetic induction. So normally I call this as magnetic field, but to follow from the book, this will be called as magnetic induction. So if you remember from electrostatic, what you would have is the Coulomb's law, and this is defined to be 1 over 4 pi epsilon 0 of q times q1 divide this by r squared times the r hat. And you could technically do the same thing for the magnetic field. So the magnetic field is pretty much similar to the electric field, but for moving currents, but for moving charges. So people tried to do experiments and they found that the force on moving charges, which we'll call as the magnetic force, is defined to be mu 0 over 4 pi times q times q1 over r squared, which is something very similar to the electric field. You multiply this by the v cross r hat, something like so. So this mu 0 here is defined to be the permeability, and in here mu 0 is the permeability of space or vacuum, and it is defined to be 10 to the power negative 7 Newton second squared over Coulomb squared. And the value is actually approximately, it is not exactly 10 to the power negative 7. So if you try to use the same idea in electrostatic, where instead of using this formula, you define it to be Q times the electric field, you could also do this. You could also do the same thing for the magnetic field, and you could define this to be QV cross the magnetic induction, where the magnetic induction here is defined to be mu 0 over 4 pi q1 over r squared v1 cross r hat, like so. This is technically 1. So now if you combine the electric field and the magnetic field, what you would get is the electromagnetic force, which is also called as the Lorentz force. The Lorentz force is defined to be Q times E plus V cross B, which is basically the total force from the electric field and the magnetic induction. So now what we can do with this Lorentz force is that you could actually substitute the forces, and what you would end up is you could have epsilon 0 times F vector. This equals to Q times Q1 over 4 pi r squared plus epsilon 0 mu 0 over 4 pi times Q1 V cross V1 cross r hat, like so. Divide this by r squared, like so. And something to note is that this section and this section should have the same units. So therefore, what we can actually obtain is actually epsilon 0 times mu 0 should be a unit which is 1 over the velocity squared. And we will call this velocity to be c squared. Now this velocity unit here turns out to be 2.9979 times 10 to the power of 8 meters per second. And if you already know about physics, this is basically the speed of light. So we will later discuss as to why the speed of light is this value, but we will do so in the future videos. So anyways, we could continue on and actually try to compare the magnetic force compared to the electric force. And maybe we want to figure out how big is the magnetic force compared to the electric force. So if we do this ratio, what we could get is mu 0 over 4 pi q times q1 v cross v1 cross r hat over r squared. Divide this by q times q1 over 4 pi epsilon 0. So therefore, we could simplify this into epsilon 0 mu 0, 4 pi, and the q's could cancel out, and what you would have is v cross v1 cross r hat, like so. Technically, at the bottom there should be r squared here, that I forgot. Now, noticing this value, there is a maximum value in the cross product, right? And the maximum should be the magnitude of v times the magnitude of r, which is, in this case, is just 1. And so the maximum will be v1, and then from v cross the v1, the maximum would be v1. and this should be less than equal to this value times epsilon 0 mu 0. And you would have already noticed this to be V over C times V1 over C. So what we see here is that the magnetic force is very small if your velocity is quite small. But then if you try to increase your velocity, there will be some relativistic component, but also magnetic force is much more stronger. So what we can also do is actually relate the magnetic induction with the electric field. And it turns out that if you actually follow the computation, the B vector here, or the magnetic induction, is equal to V1 cross the E vector, multiply this by mu 0 epsilon 0. And this would pretty much give you V1 over C cross E vector over C. So what we see from here, so with this, we could actually define what is the unit of the magnetic induction much more easily. So the unit will be the electric field, divide this by the speed. And it turns out that the unit is Teslas. So what we did previously was playing around with particles. So now we'll be handling with not particles, but we'll be handling with currents. So we will try to determine what's the force on current carrying conductor. So let's just write down again what is the magnetic force. The magnetic force is QV cross B. And we can say that this is the force on a very small object, like so. We'll call this to be dF, with a surface area, which we'll call this to be A, and a width here, which we will call as dl. And it's moving in this direction, V. And let's say that we have an amount of particles, charge carriers, which is n over a unit volume. So if we try to consider the unit volume here and then we try to figure out the force on the entire thing, what we would obtain is this would be n times a times the length of dl, right? And maybe we can call this to be a vector instead. So this is the force on a particular slice on the conductor. And what we can do with this equation is that we can actually switch v vector and dl vector, since they both have the same direction. So we can say that this is NA times the length of v vector, and Q dl vector cross b vector is the df vector. And now you could actually sum up each of these slices within your circuit, and what you would obtain is this would basically become I dl cross b, right? And you can take this with the integral. Same thing in here. This would be the f vector of this current carrying conductor. So now let's assume that the current is constant. Let's say that it only has one loop. What we could do with this equation is that we can just get rid of the I. So what we would have is this contour integral of the dl vector cross the b vector. And this would equal to the f vector. Now, if we take this one step further and assume that the magnetic induction is always the same no matter where it is, the force would be zero. Meaning that if you apply a magnetic induction on your system, if it's constant, the force would be zero. But we haven't asked about the torque. So if we try to determine the torque, which is the R cross dF, this is gonna be I times the closed integral of R cross dl vector cross b vector. And using some vector algebra, what you could get is this is similar to R dot b times dl vector minus R dot dl vector times b. So maybe we can try to consider one direction first and see what this evaluates towards. So if we consider the x direction, this would be dx of xbx plus yby and zbz, like so. And then for the other one, this would be x dx plus y dy plus z dz, everything multiply this by bx. So what we end up having is y by dx plus zbz dx, subtract this by y dy bx minus z dz bx. And there is obviously some other components in the y and the z direction, which we don't calculate because it will be very similar. So we will use the same assumption that the magnetic induction is the same for anywhere in space. So what we could end up having is this will be two different types of integrals. One of them is the one with the same variables, like shown here. This could be x dx, y dy, and so on. And there's another one which is defined by two different variables, eta and psi, like so. If you evaluate the closed contour, what you would end up having is this would equal to 0. But this one would obtain a zeta, which is defined to be the cyclic of eta, psi, and zeta. So in the x direction, this thing here would become negative az times by, and this one here would become ay bz. And then the rest will be 0 based on the integral that we have obtained here. And so if you extend this for the other components, what you could end up having is you could write this ax, ay, and az to be the vector, a vector, and you could cross this with the b vector, multiply this by the current, this will be your torque. And so we can actually combine this I times a vector, and this is what we call as the m vector, or the magnetic dipole moment. So it's the magnetic dipole moment cross the b vector would be the torque. So maybe if we look at the top side here, like as we can see here, the y dx and the z dx, this might look very similar to r cross dl because there is this cross component term. So maybe we should try to understand r cross dl integral, and maybe we should check what is the result. So if we try to expand this, this would become y dz minus z dy plus z dx minus x dz, and lastly it's x dy minus y dx. And what you could end up having in here, this would be ax, this would be plus ax again, this would be ay and plus ay, and then az and plus az. So what you end up having is basically half times the closed integral of r cross dl vector is just the a vector. So you could technically also write the magnetic dipole moment to be half times the current of the closed integral of c of r cross dl vector, like so. But we could also think about, instead of using current, we should use current density. So what we wrote here is mostly using current, but maybe we should consider current density. So instead of using I, like I dl vector, instead we could just convert this into I over A times the dl vector times A, and this would actually become pretty much the j vector dot the dv, like so. So you could end up writing the dm vector to be a half times r cross j vector instead, dv. So now let's go and discuss one of the most fundamental laws in magnetism, which is Biot-Savart. So basically Biot-Savart comes from the formula that we got earlier, and technically they did the experiment and write down the equation. But in this case, what we'll be doing is we'll just try to get a physical intuition as to where does this Biot-Savart comes from. So it's coming from this equation, and if you notice from previously, we could actually rewrite this q times v here, and if we do this for the general term, you could just multiply this by n times a times dl, and then do some rearranging. What you would end up having is this would be equal to mu 0 over 4 pi of I1 times I2 of the closed integral of the first loop and also the second loop of dl2 vector cross dl1 vector cross r2 vector minus r1 vector over r2 minus r1 cubed. And because we also know that the magnetic force is also technically could be written as I dl vector cross b vector, what we can do is that we can just group the integral above in order for us to obtain the b vector, which is mu 0 over 4 pi I1 times the closed integral of the first loop of dl1 vector cross r vector minus r1 vector divided by r vector minus r1 magnitude cubed. So this integral form looks very complicated. So instead, what we'll be using is we'll be using the differential form, which is mu 0 I1 over 4 pi of dl1 vector cross r vector minus r1 vector divided by r vector minus r vector 1 cubed, like so. And if you use the transformation IDL into JDV again, this would just be mu 0 j vector cross r vector minus r1 vector over r vector minus r1 vector cubed over 4 pi dv, like so. So from this Biot-Savart, what we obtain is the divergence of the magnetic field has to be zero. And this is the second Maxwell's equation. So with this law, you could solve magnetostatic problem. And so I won't do a full discussion here, but if you want practice problems for you to solve on your own, you could go ahead and use the description below and use it for your favorite AI so that you could get your own personalized practice problems. And if you have any troubles with those practice problems, you can go ahead and join my Discord and discuss it in the server. But anyways, there's this card at the top that you could click so that you can see how do you solve the magnetism problems. And what I want to discuss here is the application of the Biot-Savart law. And it turns out that if we engineer a wire that is coiling around, or we call it as a solenoid, what you end up having is a pretty constant magnetic induction inside of the coil and pretty much zero outside. And so this could be useful if you're trying to do experiments with the magnetic field. Thus, you could try to study the trajectory of a charged particle or so on. And also, because technically the Tesla is a very big unit, we instead use another type of unit which we call as Gauss. So Gauss is pretty much 10 to the power negative 4 Teslas, which is an alternative unit system that is normally measured throughout our daily life. So let's go back to the theoretical side and try to understand Ampere's law. Ampere's law. So what we got previously is the divergence of the magnetic induction is zero. But what about the curl? Maybe we can get more information into this. So if you try to put this into the Biot-Savart law, what you would end up having is this would be mu 0 over 4 pi of the curl of this integral j cross r dv divided by r cubed, like so. Now, if you expand this curl here, what you would end up having is this would be the integral of the divergence of r vector over r cubed times j vector minus the divergence of j times r vector plus r times the differential operator times the j vector minus j vector times the differential operator of r vector over r cubed. Now, because we are considering a steady state, we could notice that the divergence of j has to be zero. And this j vector here is also technically zero because this operator here, the nabla here, is actually operating on another set of system that is totally independent of the j vector. So we can call this to be j1 and then this nabla to be nabla 2 actually. So what we would end up with is the integral to be the integral of divergence of r vector over r cubed times the j vector. Subtract this by j vector times the differential operator of r vector over r cubed dv. This is for bookkeeping. And now because we also know what's the divergence of r over r cubed, which is actually 4 pi delta r1 minus r2, this would become mu 0 over 4 pi times, well, actually it's mu 0 of j vector. Subtract this by the integral of j times the differential operator of r vector over r cubed dv1. So what you can do with the right-hand side is that this is actually very similar to a important vector integral theorem, which would end up to be the closed integral of the surface of the j vector times the r vector over r vector length q times the n hat dA. Subtract this by the closed integral of the volume of the divergence of j vector r vector minus, r vector over the length of r vector cubed, like so, dv. And the divergence of j, we know this to be 0. And also for this one, because our j vector is bounded within the universe, therefore at the surface there shouldn't be any current density. Therefore this should also be 0. Thus we would obtain that the curl of B vector is mu 0j, coming from Biot-Savart. So we can make this into the integral form. Thus the Ampere's law would become B vector dl vector of the closed integral is equal to mu 0 of the surface integral of j vector times n dA. Now what you would notice here is that on the right hand side, j vector dot n dA is actually just current. So you could actually rewrite this as mu 0 I is equal to the closed line integral of b vector dl vector. It's basically the same thing. And this is the Ampere's law. So the Ampere's law will provide you with a much more easier method to compute the magnetic induction. So with the cards shown at the top, this is basically showing you the solution of the magnetic field on a solenoid by using Ampere's law instead of using Biot-Savart. Now let's discuss about the magnetic vector potential. So the vector potential is defined from the property that the divergence of B is 0. And because we know that the divergence of curl is also 0, we could state that the curl of A is basically B. Thus we'll define B vector to be the curl of this A vector, where A vector is called as the magnetic vector potential. So you can also try to change the Ampere's law, and this would become the curl of A vector would be mu 0 J vector. And using some identities, what you could have is the gradient of the divergence of A vector subtracted by the Laplacian of A vector must equal to mu 0 J vector. And so something to note here is that the magnetic vector potential has lots of different solutions. So what we can do is that we can try to limit the amount of solution by defining the divergence of A vector to be 0. This is not constraining any type of physics. We are just basically setting a standardized system where the divergence of A vector is 0. And we choose this so that our vector potential would have the form in the Ampere's law to be divergence of A vector to be negative mu 0 J vector. And this is pretty much giving you the Poisson's equation for the vector potential. So therefore, we could actually obtain what is the A vector from this differential equation. And it is actually defined to be mu 0 over 4 pi, the integral of the volume of j vector r vector. Divide this by r2 vector minus r1 vector. This is the A at r2, dv. So now what happens if you try to view this vector potential at a very far distance so that you don't really see the current? So if we use the A vector r vector and we'll just translate this into the IDL version, this would be mu 0 over 4 pi I of the integral of dl vector r2 vector minus r1 vector dv. No, sorry, like so. So what you could do is that you could actually do the Taylor series and so on. And what you would end up having is this would have the limit as r goes to infinity. This would become A vector is equal to mu 0 over 4 pi of the magnetic dipole moment cross the r2 vector divided by the r2 length cubed. And with this, you could actually obtain the magnetic induction just by doing the curl of this magnetic vector potential. And what you would obtain is the magnetic induction is mu 0 over 4 pi negative magnetic dipole moment over R2 cubed plus 3 times m dot R2 times R2 over R2 cubed, like so, over R2 to the power 5, like so. So the vector potential is something that is quite general, but solving the vector potential is very hard. So instead, what we can do is that we can try to define a scalar potential instead. And the way that we will do this is we need to have assumptions. And the assumption that we need to make is the curl of the B has to be 0, or this would mean that J has to be 0. So what you could end up having is B vector is equal to negative mu 0, the gradient of phi star, where the mu 0 is just for convention. And therefore, you could actually obtain what's the scalar potential for dipole. It turns out that this is m dot r2 divided by r2 cubed over 4 pi. And alongside that, when you actually use the m, this is actually I and dA, right? So if you substitute this in and do the integral, this would be the integral of I times n dot r dA divided by 4 pi r2 cubed, right? Now, something to note is n dot r2, and something to note is n dot r2 divided by r2 cubed is actually the definition of the solid angle. So therefore, what you could actually obtain is this is I over 4 pi times the solid angle, the omega, and this is for each of the small dm's. So if you sum up the entire magnetic dipole moment, you would get this to be I over 4 pi of the solid angle. Well, it is technically negative to be precise because of the conversion from R2 towards the R vector. Lastly, what I want to discuss is the magnetic flux. So the magnetic flux is pretty much defined from the divergence of B is 0. If you do the integral form, this is just the closed integral of the surface B ds vector is equal to 0, right? The closed. So you could define like one of the sides, the open side, B vector ds vector, is not always 0, which we'll call as the magnetic flux. And that's pretty much all about magnetism that I could discuss in this video. So next video we'll be discussing about magnetism, but in materials. So thank you very much for watching. Make sure to like and subscribe so you won't miss the next video. And also join the Discord so we can do more discussions about certain problems or physics that you want me to discuss. And also use the description to get practice problems so that you can understand physics better through practice problems. Thank you very much, and I will see you on the next video.